Hey guys, I want to make a short video showing you how to do a certain class of projectile motion problems. And in this particular kind of projectile motion problem, the initial height is different from the final height. And so this is a little bit of a generalization of some of the problems that you've been doing that are example problems in your book, and usually easier problems where the initial height is equal to the final height. So let's draw a picture of the situation and set up some variables and do this as an example. Okay, so the problem looks like this. Here's the picture. So we've got, let's imagine we've got a ledge, okay, and I start the projectile, I fire a projectile from the edge of the ledge at some initial velocity v0, okay? And that initial velocity vector makes an angle, let's say theta, with respect to the horizontal. And I'm going to assume there's some initial height, y0, that it is launched from. That's the height of the ledge, okay? So what happens is this projectile follows a parabolic trajectory and then lands somewhere at some final x sub f. And the full coordinates of the final coordinates of the object would be x sub f 0. I'm going to assume that the ground is at y equals 0. So its vertical position ends at y equals 0. Its initial vertical position is y0. And I'll also assume, for simplicity, that this initial x0 is equal to 0. So this point here is the origin. Okay? So what do we want? What we want to calculate is the range, delta x. And in this case, since delta x is equal to, delta x is defined as xf minus x0, x0 is 0 here, so in this case, delta x is just equal to xf. Okay, so that's this distance. So how can we find how far this thing goes? Let's write down what we know. So we know the entire initial velocity vector. So to make this problem a little more concrete, let me give you some numbers that may make the calculation a little bit easier. Okay, so I'm just going to use some simple numbers here. I'm going to assume that the initial velocity, the initial speed, v0, is 4 meters per second. And let's choose a simple angle. Let's say theta is equal to 30 degrees. And let's assume that the initial height, y0, is equal to 1 meter. Okay, and I'm going to try to do this problem using these relatively simple numbers. So immediately we can go ahead and say a few things about what the initial velocity vector is. v0 vector is going to have a vertical component and a horizontal component. The horizontal component is the x projection of this vector. So this is v0x, and then this is v0y, the vertical component. So v0x is going to be v0 times the cosine of theta, x hat. And then I need to add that to v0y. v0y is v0 times the sine of theta, and that's in the y hat direction, so I multiply it by a y hat. And so that's my full initial velocity vector. And I know v0 is 4 meters per second, and theta is 30 degrees, so I can calculate what these numbers are. v0 vector. Well, actually, let me just write it as the two different components. v0x is going to be v0 cos theta, so that's 4 times, and then cosine of 30 is root 3 over 2 meters per second, so this is 2 root 3 meters per second. And then v0y is equal to v0 sine theta. And so that's going to be 4 times sine of 30, which is a half. So that's just 2 meters per second. Great, so I know what these guys are. That's going to be useful. Now let's write down the other kinematic equations. Let's go ahead and write them all down, and then we'll see which ones are useful and which ones are not. So let's start with the x equation. X is equal to x0 plus v0x times t plus 1/2 a sub x times t squared. Now, because this is a projectile motion problem near the surface of the Earth, a sub x is 0. So this is 0. I have no acceleration in the horizontal direction. I know y is equal to y0 plus v0y times t. And I know ay is equal to minus g. So I'm going to plug that in. So I have a minus 1/2 g t squared. Okay. And I also know v sub x is equal to v sub x0 plus a sub xt. But again, a sub x is 0, so that term is gone. This is just saying that v sub x doesn't change in the horizontal direction. It's always equal to its initial value. And I know v sub y is equal to v y0 minus gt. Okay, great. So which one of these is useful for calculating the final position? Well, x will give me the final position because I know x sub f would be x0 is 0. I can get rid of that. v0x times t final, if I knew what t final is. So this is the one thing I don't know. I could use this equation, but I would have to figure out t final using a different formula. Right? So we're gonna underline this formula and come back to it a little bit later. We do need to figure out some way of calculating TF. So let's look at the other formulas we have and see which ones might be useful. This one here would be useful if I knew what the final velocity was at the final time. And I don't know that. So this one, not so useful. Okay, this formula doesn't even have a t in it anymore, so it's certainly not useful for calculating TF. The only one I could possibly use is this one, the y equation. So let's write that down. I have y final equals y0 plus v0y times t final minus 1/2 g t final squared. So what do I know in this equation? I actually know y final is 0 because the projectile lands at the ground again. It lands over here at 0 height. And I know y initial, y0, is 1 meter. That was given to me. And I know v0y. I calculated that above. v0y was 2 meters per second. And I know g, so I know that this coefficient here, including the minus sign, the coefficient to the t squared is minus 1/2 g. Well, g, I'm going to approximate g as 10, so this is minus 5 meters per second squared. So how can I solve this? This looks like a quadratic formula. So I can use the quadratic formula. Remember, the quadratic formula says that if you have a formula of the form ax squared plus bx plus c equals 0, then the solution is x equals minus b plus or minus square root b squared minus 4ac divided by 2a. So we all remember that. And what are my various constants a, b, and c in this example? A is the coefficient of the thing squared. In this case, the thing is t sub f. So that's this thing. So this is my A. And I know that B is the coefficient to the T sub F, so this is my B, and then this is my C. So let's plug it in and see what we get. So we get T sub F is going to be minus B, so that's minus 2 meters per second, plus or minus square root. B squared is 4 meters squared per second squared. Units get squared too there. And then minus 4 times A, which is minus 5 meters per second squared, times C, which is 1 meter, all divided by 2A, which is minus 10 meters per second squared. Okay, so let's simplify this expression. Inside here, inside the square root, all of this stuff, let's see, I've got minus 4 times minus 5, so that's plus 20 times 1. So 20 plus 4. So this looks like it's going to be about 24. And what are the units? The units are going to be meters squared plus seconds squared. And that's all still inside the square root there. So I'm just gonna, I don't really, I'm just doing this as an approximate example here. So I'm gonna try to make this easy. I'm just gonna approximate 24 meters squared per second squared as 25 meters squared per second squared, so that I can take this square root easily. 24 is almost 25. The square root of 25 is 5. And so the square root of 24 would be like 4.9 or so. And I'm going to round that up to 5 anyway. So let's go ahead and put all that in. So I've got T sub F equals minus 2 over minus 10. So that's plus 0.2. And then the units, let's see, I've got meters per second divided by meters per second squared. So all of the units are going to work out. So this is going to leave me with the seconds upstairs. And then I've got a plus or minus square root 25, which is 5 meters per second, divided by a minus 10 meters per second squared. So again, these units work out so that I'll have 1 unit of seconds upstairs. So this is plus 0.2 seconds and then minus plus 0.5 seconds. Okay, so I have 2 possibilities here. I've got a TF that could be minus 0.5 plus 0.2, so that would be minus 0.3 seconds, or plus 0.5 plus 0.2, so that's 0.7 seconds. So these are my 2 possibilities. Why do I get 2 numbers, and which one should I choose when I plug in to my formula for x final up here? Which one should I choose? Well, I get 2 numbers because I'm solving for the time at which my projectile has a position of y0. But there are 2 possible times that this parabola intersects the y equals 0, the x-axis here at y equals 0. One of them is the physical time that I want. That's this one. So this is the physical time. This is really what the time at which I care about. And then if I had followed this parabola back in time, it would have intersected y equals 0 here at this earlier negative time. So this is at t equals minus 0.3 seconds, and this is at t equals 0.7 seconds. And this is the one I care about. So now I'm ready to plug this back in, right? So now I can have my xf was equal to v0x times t sub f. And so this was v0x was what was it? It was 2 root 3 meters per second. So 2 root 3 meters per second times TF is 0.7 seconds. And if you want to go ahead and plug that into a calculator, let's see, we get about 2.4 meters. And notice the units work out, right? So these units cancel so that I'm left with 1 meters here. So this is our answer for the range, how far this thing goes. That's this distance. Okay? So I hope that this is helpful. This is how, in general, you can do these kinds of problems. The procedure, you know, every problem is a little bit different, but I hope that this gives you some insight into how to think about them and set up these kinds of problems. Thanks for watching.